important conclusions. So, the floor.
Thank you, Mr. President of the jury. And I would also like to thank the audience to have come to this PhD defense, as well as the member of the jury that assists to it remotely and physically. And first, when one talks about aeronautical gas turbines, one must talk about the climate change that is occurring at the moment, which consists in the fact that temperatures are rising due to the fact that the human being release a lot more greenhouse gases, such as carbon dioxide or methane. And this has two main consequences. First one on the environment, for example, the sea are rising because the ice is melting, and there are longer heat waves. And this also has some consequences on the human beings, that is to say the population are more moving, there are more and more water and food crises, and diseases are about to multiply. Concerning the transportation sector, here is a graph concerning the anthropogenic emissions by sectors. And for the transportation sector, it's about 14%, which are mainly due to this reaction, which is the combustion reaction with the air of an hydrocarbon that is giving carbon dioxide and the water, which are greenhouse gases. Among this transportation sector, we have the civil aviation accounting for 13% of the total CO2 equivalent emission, which represent 1.8% of the CO2 released. But we have also to take into account other effects due to other pollutants, such as nitrogen oxides, carbon monoxides, soot, sulfur oxides, or unburned hydrocarbons, which then account for a total of 3.5% of the total radiative forcing on the Earth. And this has to be put face to face with the traffic expectation that is expected to rise in the coming years, as you can see on this graph, representing the number of passengers for the different years to come. And therefore, there is a need for improving our airplane. And this is made by improving our power sources, which then must remain possible, safe, and sustainable. That is to say, to release less pollutant than fossil fuels. And we have three main strategies at our disposal. First one would be the use of batteries. But as you can see on the graph on the left, which represents the volumetric energy density as a function of the gravimetric energy density, batteries, they have one order of magnitude below the liquid fuels that are used commonly in aeronautical gas turbine, meaning that we would have to carry 10 more time the weight of it, which would be not suitable for aeronautical aviation. Second, we could think about hydrogen, but the technology is not ready at the moment to put hydrogen in a current aeronautical gas turbine. Therefore, we will go to sustainable aviation fuel, or SAF, which are a short-run available solution that we could use at the moment. To define what is a sustainable aviation fuel, one must first define what is conventional kerosene. So here you have the average formula, which is about 10 carbon and 20 hydrogen, but it's mainly made of different types of families, such as 60% of alkanes or branch alkanes, 20% of cyclic species, and 20% of aromatics. Sustainable aviation fuels, they are usually made of alkanes and branch alkanes, so they will burn mostly the same way. But the idea here is that the feedstock that was grown to produce those sustainable aviation fuel has already taken part of the carbon dioxide, and then in the total life cycle, it will reduce the emissions that have been made. There are several paths that are here taken into account, and the most well-known are the one producing HEFA fuel from oil feedstock and alcohol to jet fuel from sugar and starch feedstock. This brings me to talk about the jet screen project that funded this thesis, and of which the goal was to create a fuel database based on a fuel matrix with a given intrinsic property and an experimental and numerical work from the industrial and laboratories that took part to this project to study pollutant, extinction, ignition, pumping system, and every other system that could be thought of. And we are going to interest here to this area in the engine, which is located between the compression zone and the exhaust gas zone, which is the combustion chamber. In this PhD, the objectives was to study the flame stabilization and the lean blowout, meaning the blowout by fuel depletion on one conventional fuel and two alternative fuels. If we come back to the combustion chamber, here is a sketch of it. So we have primary air that is mixed with fuel through an atomizer that is often pressure swirled to allow for two different zones to be accounted for when the flame is stabilized. That is to say, the outer recirculation zone and the inner recirculation zone over here. Then droplets, they are injected in the combustion chamber at the liquid form, and they will evaporate before or in between or after the flame front, and then giving high temperature that we then lose heat through the walls and be cooled down by the air, and then be released through this exhaust duct as burned gases. This means that we have several phenomena that we must account for. Turbulence, for example, induced by the high motions of the combustion chamber, the spray, the fact that it's both liquid and gaseous system, and the combustion that relies on chemistry, which then we need to use the larger dissimulation to account all of that with a compressible multi-species code such as AVBP. And this PhD goal is to look at the fuel effect. Therefore, we will have to look both at two main aspects of these sustainable aviation fuels, which are the chemistry and the spray. This brings us to the plan of the PhD. So first, after introducing the spray stabilized burner from the GLR that was experimentally and numerically simulated at GLR, we will talk about the lean blowout. Then we will talk about fuel comparison between the one conventional fuel and the two alternative fuel. But first, we have to look at canonical processes concerning the chemistry and the two-phase flow. So first, we are going to see the chemical single processes and going to go from the experiments to how should we model kinetics in our engine. And that's the data that we received from the experimentalists. So it's a GC-GC matrix. And the idea is that it's a mass percentage of every species classes per carbon number. So each bar here represents one species. And we can't afford to take all of these species in a multi-species code such as AVBP. So therefore, we have to construct a multi-component surrogate model, and that's what Polyme did with this real fuel. And they do that to emulate the properties of this real fuel. So how do they do that? First, they pre-select a fuel palette with several species where they know the properties that they want them to emulate the real fuel. And they choose objective function, so chemical objective functions such as the H/C ratio and the composition, and physical properties, so the distillation curve or viscosity or density, for example. And then they arrive to a final surrogate definition, which here for jet A1 considers endodecane of 60%, methyl cyclohexane, which is a cyclic species of 20%, and xylene, which is an aromatic species of about 20%. Jet A1 in this defense will be used as a reference fuel and will always be displayed in blue in the following slides. For the two others alternative fuel that we are going to see, the first one is the alcohol to jet fuel, which is here composed of branch species, mainly isododecane, but also a little bit of isooctane and isocetane, and which will be displayed in red. Finally, there is a high aromatic fuel that was created for JetScreen to look at the influence of a lot of cyclic and aromatic species on a surrogate mechanism, and which is composed of a double cycle species diclene of about 60%, a branch species isododecane about 20%, and a double aromatic methyl naphthalene about 20%. And it will be always displayed in green. If we look at the properties of those, how those surrogates will compare to the real fuel, one can look at the distillation curve here and the laminar flame speed over here. And there, one can see that between the blue and the red curve, there is a good match, and that the sensitivity is retrieved for both properties. However, for C1, it's much further for the distillation curve, and there were no data at the moment for the laminar flame speed. A second aspect to be taken into account is the reduction of the model, and it often goes through the fact that we receive some detailed mechanism, kinetic mechanism from the experimentalist that simulates how reactants goes to products with a lot of intermediate species. So usually these mechanisms for heavy fuels are above 100 species, which is not affordable for us again. So we have to use what is called a reduction code to be able to use some mechanism that contains less than 40 species and that are then usable in AVBP. Here at Cerfacs, we are using Arcane. That is an upper layer from Contra, which is an open source kinetic solver that would rely on equilibrium, time evolving reactors, and flame. So how is Arcane working? Here we input to the code a mechanism, fuel, and operating conditions, as well as a target species and maximum acceptable errors that relies on those cases here under. And we will apply three techniques. First one being the species removal with a direct relation graph with error propagation, meaning representing the species and the reaction and deleting the weakest species and reaction that don't take into account to the greatest path. Second, we are going to lump the species. So if there are isomers, they can be lumped. And if in between after having applied those two steps, then we have a skeletal mechanisms, but this mechanism is still too stiff temporally and still contains too many species to be used as such in AVBP. Therefore, we are going to apply a third technique, which is a quasi-steady state assumption, which then relies on the fact that species are reacting very fast, and we can approximate the source term this way so that an algebraic relation may be found to calculate the species A. Which means that it's still contained in the mechanism, but not in the transported species, which reduces then the number of species for using the scheme in AVBP. And this final scheme is called an analytically reduced chemistry or ARC mechanism. So we are going to do that with the polymy mechanism here, which contains 368 species and 14,000 reactions, roughly, and applied our reduction step to these cases, so a time-evolving reactor with an ambient pressure, a stoichiometric equivalence ratio, and an auto-ignition time. We want the auto-ignition time to be below 15%. And for the premixed flame, we chose an initial temperature of 400 Kelvin, an ambient pressure, lean stoichiometric and rich equivalence ratio, and we want the laminar flame speed as well as the carbon monoxide final and maximum mass fraction to be below 7%, the final products to be below 2%, and the final temperature to be below 1%. And here are the results obtained for our three mechanisms, A1, B1, and C1. So for ARC A1, we have 36 transported species, 16 QSS species, and 543 reactions. For B1, 31 transported species, and for C1, 35 transported species, meaning that we've reached our goal, which was to reduce our scheme to be below 40 species. We have to say that for C1, the errors have been multiplied by 2 to be able to reach this target error. So what we can look for then is what are the species that are finally kept. And here we have done this exercise for A1, where we have the fuel species and dodecane methyl cyclohexane and xylene, the air, the main products, CO, CO2, and water, other intermediate species, but the most species that there is in the mechanism are the decomposition species here. And if we represent the fuel pathway that follow the C8 atom over here, one can see that they have several paths from the red species toward the CO and CO2 and other species, and that there are common pathways here for methyl cyclohexane and dodecane, for example. The most important species are completely comprised in the endodecane mechanism, while for xylene it's much more reduced because it starts from a molecule with a different structure, which means that the more different will the species be, the more pyrolysis species there will be in the mechanism. Also, this could be lowered by using iChem methodology and then suppressing all these links by reaching only the species with the small carbons. When one is going to the results, then one can look at the final state of our mechanisms through different equilibrium. And here we can clearly see that fuel are sensible to the EH over C ratio here. That is, has been put in the order of increasing. We can see clearly that the water content is increasing, while the temperature at the end of the combustion is decreasing, and the carbon dioxide and carbon monoxide mass fractions are also decreasing, meaning that as C1 is the one containing the most aromatics and cyclic species, it seems that it has a lower combustion efficiency. So we have these fuel sensitivities, but one must not forget that there is also a sensitivity inside each fuel. And when representing the adiabatic final temperature as a function of the equivalence ratio, one can see that clearly aromatic species are the ones that are showing the most different at final temperature compared to other branch species or cyclic species. When going to the kinetics, we can look at the laminar flame speed as a function of the equivalence ratio, which is displayed here for the three-fueled compared to the detailed mechanism with the symbols. And one can see that the fuel sensitivity is recovered, even if for B1, the curve is slightly above the detailed mechanism curve, but still within the error that we targeted for arcane reduction. We can go further by introducing the fuel effective ratio here on a time evolving reactor to understand which are the zone of influence of our fuel, which is here introduced as being the ratio between a fuel species equivalence ratio divided by a total equivalence ratio. And here, for example, what you can see that we start from endodecane being almost 60% of the total equivalence ratio, methyl cyclohexane being 20% and xylene being 20. And you can see that endodecane, while being the majority species, is very quickly consumed before cyclic species, and then before the xylene, the aromatic species, which is very long to be decomposed. Here, for B1, we can see that they are all branch species, therefore they are much fast consumed. And for C1, we retrieve the same conclusion, being that the branch species is very fastly consumed compared to the cyclic and aromatic species. When one then goes to pollutant, they were estimated from the detailed mechanism polyimine NOx, as it was not the primary goal of this PhD to estimate the pollutants. But here you can see that we retrieve the order we had said earlier on, that is to say that the species with the less aromatics produces the more carbon dioxide or CO2. For the maximum value of carbon monoxide, you can see that it's roughly the same for the three-fuel, even if it's slightly lower for B1, but it seems that it's more rising with the richer the equivalence ratio is. And for the maximum of NO, one can see that it's roughly the same for A1 and B1, while it's increasing for C1 fuel. Soot, we are not evaluating in this work, as it would require a much more complex setup. To be noted that these two species, so the level of NOx and of soot, will not be evaluated, will only be evaluated in the ARC scheme, but not computed, as they are not present and were not targeted. So now that we've seen the chemical processes, we can go to the two-phase processes, seeing how from the models and vaporization properties, we can go to spray flames to test these two-phase processes. And first of all, there are two modeling that exists in the literature. First one is a discrete modeling, that is to say that we will evaporate every species here represented with a bar, which may be costly, but is simpler to code and better suited for fuels containing a fewer species, like B1, for example, here. And there is another method, which is the continuous model, which here relies on probability density functions and will check the species compared to their molar mass to be able to evaporate them. This representation enables the representation of a lot of species with a very few computational effort. However, the coupling with the gaseous phase may be more tedious, as the gaseous phase cannot represent such a number of species. Therefore, the discrete model was chosen for this study. And to look at the performance of this model, we are going to look at the diameter squared evolution on a single droplet evaporation and compared to an experiment made at the DLR, sorry. And here we can see the diameter evolving at the function of the time for the experimental work with symbol and for the numerical work as a line. One can see that the final evaporation time is retrieved for both, as well as the fuel sensitivity, meaning that A1 and C1 over here are evaporating much longer than B1 does. And there is also a sensitivity to each fuel species when one goes into the liquid mass fraction inside every droplet. One can see that here, for A1, for example, methyl cyclohexane is the first one to evaporate, followed by xylene, and then the last one is endodecane, which means that there is a preferential evaporation that is occurring between the fuel species present in our droplets. For B1, we will have isooctane evaporating the first, then isooctane, and then isocetane, which is the last one to stay. Then, for C1, we have isooctane and decalene, that are evaporating slightly at the same time, and methyl naphthalene that is the last one to evaporate. And this single droplet evaporation would enable us to go in a more complex case that would involve also chemistry, which would be a 1D spray flame. So here is a setup of this spray flame where we wanted to fix these parameters with a temperature of 50 degrees, an ambient pressure, and a total equivalence ratio of 0.8. And the idea then was to inject a part of this total equivalence ratio through gas or through liquid, with three cases, first one being totally gaseous, second one being semi-gaseous at approximately a liquid equivalence ratio of 0.3, and the last one being totally liquid equivalence ratio. And what we can see first is to retrieve our ratio, comparing our fuel species equivalence ratio to the total one, to see the zones of influence. And one can see that it has completely reversed the order that we had for the gaseous flame. So here, xylene was the last one to be consumed. However, for the other cases, as we evaporate endodecane, the last one, then it will be the last one to be consumed. It's almost the same conclusion for B1, where it's completely reversed, but it will have a lower impact as isododecane is the fuel that has the most concentration in the original fuel. And for C1, the order remains the same. This will change the properties of the flame, and we can look at how it changed, for example, the laminar flame speed here. And it's already very tedious to calculate it when going towards more liquid equivalence ratio. It's different from the free gaseous one, sorry. And you can see that the preferential evaporation case over here will not have the same impact on how the laminar flame speed is evolving. And for example, if we take the case of A1, we can clearly see that the fact that it's lowering the laminar flame speed is the fact that endodecane will burn in hot gases, which will be then less efficient than if we would burn at a purely gaseous flame, and then would change the dynamic of the flame. Concerning the pollutants, CO2, the final mass fraction of CO2 stays the same and is not displayed here. Here you have the maximum of carbon monoxide as a function of the liquid and gaseous equivalence ratio. And one can see that it hasn't got a lot of fuel sensitivity, except it increases with the equivalence ratio. Finally, NO were not evaluated here, but they are expected to increase as for CO, the flame front is becoming richer and then will increase those NO mass fraction. So once we've seen both cases, so the chemical processes and the two-phase processes, we can go to the burner and present how it was developed from its presentation with the experimental work to the flame structure. So here is the SSP burner from the DLR, where they have been computed it experimentally. So the fuel is injected over here, the air is injected over here, and is going into the swirler, which is composed of two stages. A first one that will atomize the droplet that are coming from the injected tube, which then will film on the boundary and then be atomized again here on this with a second stage of atomization. and then the gas will be released in the outer duct here. The operating point that was chosen was here a gaseous temperature of 50 degrees, a fuel temperature of 30 degrees, an ambient pressure, and a lean equivalence ratio of 0.8. And the idea is that this point was chosen because there were numerous experimental data on jet A1 and a few on alcohol to jet, as we will see further on. We computed this chamber with a VBP. We applied it on a convective scheme using Lax-Vendroff of second order, a diffusion scheme that is second order finite element, an SCBC boundary condition model, Whale model for the subriscale model, and a thickening flame turbulence model that is based on the heat release rate and with a Takeno sensor, with a constant Charlotte efficiency model. Concerning the walls, either thermal walls with the relaxed coefficients were applied on the combustion chamber and on the base plate. All other walls were considered as adiabatic, and the droplets are filming on the swirler walls and sleeping on every other walls. For the chemistries, we used a BFER mechanism that contains 6 species and 2 reactions, and that would emulate the properties of kerosene, such as the laminar flame speed, the auto-ignition time, and final temperature, and produced mass fractions. And from these calculations, we started the 3 arc calculations, A1, B1, and C1. Finally, the two-phase flow was started with an earlier Lagrange methodology with an evaporation model from Abramson and Sirignano, a drag model from Schiller and Neumann, and a discrete multi-component, as we said earlier on. The injection was realized with a femur model with a Rosin-Ramler injection that was determined with an optimization study. So here is the flame structure of the structure of the flame that we obtained, where we can clearly see the axial velocity field here with the outer recirculation zone and the inner recirculation zone. The convective time step is about 5 milliseconds, and this will be useful for the following, as we will see. This induces this following shape of the flame. So here we have represented the positive heat release rate field as a logarithm with a logarithm scale. And one can see that there is a high activity on the outer recirculation zone and a little bit on the walls, and that the flame is M-shaped with a weak central branch over here. And this leads to the following temperature field, where we have so a high activity in the outer recirculation zone, which is then re-injected in the flame by the IRZ and the ORZ at respectively the top and the foot of the flame to reheat the flame. Also, we have performed the different contours of equivalence ratio here, seeing that the flame is richer when the temperature seems to be higher. So once we've done that and presented the flame structure of the SSP and the setup, we can go to the lean blowout phenomenon, and first present the experimental procedure that was realized at the DLR. So they started from a stabilized flame here, and they decreased the mass flow rate by steps to go to 80 grams per hour below the expected lean blowout mass flow rate. And then they realized a ramp that was done with a steady rate that lasts about 200 seconds to reach the LBO. And they reproduced the results 3 times to be able to have the following results over here, which they had at a lean blowout equivalence ratio as a function of the air mass flow rate over here. And what we can learn from these curves is that alcohol to jet fuel seems to resist less than jet and A1 and high aromatic fuel. We are going to focus on this point here, which is the operating point chosen, and which shows an equivalence ratio at LBO of 0.49. However, 2 seconds of simulation is very big to compute, and therefore we are going to apply another methodology based on approximations. And this is what we want to do here. So we have started it with the BFER mechanism, and you recognize the former experimental curve that I presented earlier on, and the numerical framework we wanted to apply. So first of all, a first step to go above the experimental LBO, and then several steps to be able to reach the lean blowout without taking too much time. And we wanted to converge between 4 convective time steps to be able to, for the flame to stabilize. However, we are not sure that the value we will get numerically would be this one. So first we will go through different steps to see where is our numerical value. And here you have the results at the temperature field. And what you can see is that the case under are almost extinct, and the case above are almost continue to ignite the flame, which means that the Lin blowout limit would be computed would be between 0.35 and 0.45. And to look further, we are going to see different interesting variables that one can compute. So here we have some maximum variables, such as the maximum temperature and the maximum of heat release. And here, mean variables that have been taken on this box here to avoid effects that could happen on the burn gases. And what you can see first is that for the maximum variable here, there is an abrupt change for the cases that are extinct compared to the cases that still are ignited. So here 0.45 and 55, which are the darkest color, and lighter color for the other fuel. And for the mean variables, you can see that source terms seem to stabilize very quickly compared to the mean temperature field, which seems here to be continuing to decrease, which means that 40 milliseconds seems to be small for the flame to converge, and therefore this calculation will be computed further. So here we have first put some different fields concerning the near blowout flame. So you have here the fuel mass fraction, and here the heat release positive with the logarithm scale with control of thickening. And what one can see is that here it seems that the pre-evaporation is longer, and it also seems that there is less heat that is released and more thickening over here because we are reaching a coarsened area of the flame. Finally, we have averaged the temperature for different heights here for different boxes through the time. And what we can see that the flames seem thermally converge around 50 to 60 milliseconds. So we can wonder why is this time so long to be converged. And therefore, we have looked at the different timescale with respect to what could occur with Lin blowout. So here we have the flow timescales above and the reactive timescales under. When we look first at the reactive timescales, it seems that the autoignition timescale and chemical timescale will have a small influence because they are very fast, and it's the evaporation timescale which will really monitor the flame. Whereas when we go to the flow timescale, here we have represented the swirl timescale based on one round of a particle, half convective timescale, and the outer and inner recirculation zones timescales. And what you can see here on those two movies is that here the zone that is of high temperature is the zone where the droplets will be ignited. Therefore, it's really the zone where the outer recirculation, it's really the outer recirculation zone that has a big time scale and that will monitor how the flame will extinct. With two-phase flow delay that will delay the extinction, and which explains thus why it takes such a long time. Therefore, we cannot apply the approach that we wanted to take at the beginning, and we must change. And what we decided is to ignite the domain on different fuel mass flow rate, and then see if the flame would stabilize it or not. And that's what we did for two cases, with a flame at an equivalence ratio of 0.40 and another one with 0.45. Where here the flame seems to be extinct, while here it seems to be sustained. That's what we can see on the different variables. So here the mean heat release rate, and here the maximum temperature, which seem to be sustained for the phi equals 0.45, while it seems to be extinct for the other one. However, when going further in the computation, it seems that this case is also extinct, which testified on the difficulty to capture a Lin blowout for two-phase processes. And finally, the LBO limit was found to be roughly above or at the same level at 0.45, which is almost the same, which is not that far from the experimental LBO. So now that we've gone through the Lin blowout, we can go to the comparison of the different fuel. And first of all, we can compare them to the conditional loading, so meaning the probability of finding a droplet in a located area between A1, B1, and C1. And one can clearly see that B1, as it was said before, will evaporate sooner than the two other fuels. And that's what can be also tested here when we look at this line above at 25 millimeters above the injector, where you can see that here the total mean diameter is higher for A1 and C1 than for B1, meaning that the fuel sensitivity is retrieved from the canonical cases. Also, here you can see symbols representing the experimental value, saying that we are not that far from it. When looking at the heat release rate fields, so here the experimental heat release rate flame, and here the numerical heat release rate that is integrated through different planes, you can see that it looks roughly the same, except that here the flame seems to be a little bit shifted upwards than the experimental flame. And there is a difference between A1, C1, and B1 seems to have its higher zone of activity being slightly shifted outwards than from the other fuels. When we look at the average heat release rate line, we can first compare the experimental A1 curve to the numerical A1, where we see that the flame is shifted toward burn gases. And between A1 and B1 experimentally, you can see that B1 seems to be shifted toward the burn gases compared to A1, which is retrieved numerically with a lower extent. C1 heat release rate seems to be thicker than the other fuels, but seems to be located roughly as A1 is. When looking at the temperature radially average profiles, here you can see that compared to the experimental value, we are also under a little bit underestimating them. But here we have A1 and B1 having a lower temperature than A1, which has been retrieved numerically also with a lower extent. And if we look at the average temperature lines over this line, we can see that here we also retrieve this behavior, and C1 being a little bit higher than the other fuels. Now we have to explain where this difference comes from. And to do that, we are going to introduce this variable, which is the instantaneous fuel mass fraction, which would account for the fuel mass fraction and the mass that is still available to burn over here. And we can then construct our ratio over here that is comparing the fuel species instantaneous mass fraction compared to the total one to look at the different zone of influence. And that's what we can see over here. So here you have a Maxwell triangle that are representing the different zone of influence. And you can see that, for example, for B1, it's quasi-monofuel, as we already said, with isododecane being nearly the same, the only fuel to dominate the flame. For A1 and C1, it's much more stratified, where you can see that cyclohexane has first burned because it's the first one to evaporate, then progressively replaced by xylene over here and by endodecane that is burning in the outer recirculation zone. For C1, you have first isododecane that is burning and progressively replaced by decalene, which is the fuel that is dominant in the initial composition. And then on some points replaced by methyl naphthalene, and other points being still decalene, being monitoring the two-phase flow field. Meaning that we can see with this representation the influence of the spray with some polydisperse effect highlighted that were not present in the 1D spray flame. The question is, how does it impact the thermal field? And to look at how does it impact the thermal field, we are going to introduce a new tool, which are those triangle plots. For example, on the square over here, we have the initial composition in mass fractions. So here, 71% roughly of endodecane that you can see over here, 15% of xylene that you can see over here, and 14% of methyl cyclohexane that you can see over here. And this represents a scatter plot with a probability density of the point where they may be located the most in the burner. And you can see that for A1, it's much further from the initial composition here and very widespread in all the triangle. And here on is the same plot, but with the point that are featuring the temperature. So the more yellow it is, the higher temperature it is, and the more black it is, the lowest temperature it is. And we can relate that to the previous graph we saw. So for example, here with methyl cyclohexane that is dominating the root of the flame, which is cold. Here, the xylene that is burning as monofuel on the edges that will burn at high temperature. And finally, those zones where it seems that droplets are burning on the far field, which are represented with this line that is accounted for with the instantaneous mass fraction field I introduced later on. When looking at the other fuels, one could see that for B1 is roughly the same consequences that as we said before, that is to say that the composition is very close to the initial one, while for C1, the composition is also very close to the initial one because there is no reverse order between the evaporation in the kinetics as for A1. And you can also see this line over here, which is at higher temperature and represent the two-phase flow burning. So if we sum up what we just saw, we have two-phase flow effects that are influencing the chemistry, where the chemistry will be applied by a pre-evaporation effect and by a preferential evaporation effect. And this chemical effect will apply heat release differently and being kinetically, let's say, more quicker or not in some location to influence then the thermal effect of the flame. And those effects were already seen on the 1D spray flame, but these effects were not seen on the 1D spray flame, which are the polydispersity and the thermal losses. And the thermal losses induce that the temperature of the gas is lower, and therefore droplets burning in the far field may induce a surplus of temperature that may increase the global temperature of the burner for A1 and C1, which then explains the fuel sensitivity of the flame. Finally, when looking further at the flame, one must look at the combustion regime, which is here tackled by the Takeno index, that here was chosen to be equal to the sum of the fuel species and the pyrolysis products to be able to account for this area here, where a lot of chemical activity is occurring, but without them obvious need to be the fuel, as the fuel would have pyrolyzed in some cases. And here you can see that there is a premixed flame that is represented in white color, diffusion flame that is represented as the darkest zone, and the stoichiometric equivalence ratio here that is displayed as a red contour for A1, B1, and C1. And as one can see, A1 and C1 seems to have much more extended diffusion zone than B1, especially because of the two-phase flow burning. But B1 has a stronger diffusion zone, and they go much further for real diffusion flame, which then influences also the pollutant emissions here, where surprisingly A1 and B1 seems to have roughly the same order of pollutant emitted compared to C1, which was a little bit contrary to what we saw on the chemical effects, for instance. The final CO2 mass fraction is found to be really close to the equilibrium value and is not represented here. And one go to the maximum of NOx mass fraction, one can see that it would not be evaluated here, but it would be expected to rise for A1 and C1 flame as the temperature is higher for those two cases, and thus it would increase the NOx values. To conclude, one can say that this PhD has enabled the development of practical guidelines for the sustainable aviation fuel definition with three main principles. First one would be that the H/C ratio should always be maximized to be the more chemically efficient possible, meaning that there should be linear and branch alkane in the mix and not most of aromatics and cyclic species for the flame extinction and stabilization. Second, that the diameter should be kept optimum, that is to say low enough to avoid the NOx and the CO and the carbon monoxide production, but high enough to resist to the Lin blowout limit. And finally, that the pre-evaporation should be of the same order than the kinetic to avoid a loss in the kinetic dynamic as we saw for A1 here. And this leads us to the conclusion that HEFA would be a good candidate for the use of those three principles for real aviation fuel. And this was possible because the framework and the tools that we saw today have been set with this PhD for the analysis of sustainable aviation fuel. And this could lead us to go further on several topics. First one would be then to conclude on the LBO methodology and to apply it to multi-component fuels to be able to see the fuel sensitivity numerically for lean blowout limit. Second, to look at the different fuel sensitivities for the pollutant emissions, and because it has only been evaluated in this work, but NOx and soot emissions could be evaluated with scheme developed for it. And finally, we with this PhD, we tackled problems for heavier alkanes and fuels. But one could think about, let's say, having some blends of those heavy fuels with some light fuels, for example, hydrogen and methane, which would consequently change the flame shape, but of which the analysis would be possible with the tools we just set up. Also, something that would be interesting would be the studying of the oxygenated species here. That would be something interesting to see on how they behave in a real combustion chamber and how they burn. So that ends my presentation. Thank you for your attention.